Problem 4. The carbon decays according to the following relation. Carbon decays to nitrogen by the beta minus decay, okay? By beta minus emission. What I mean by beta minus, it's an electron, okay? Plus neutrino. Anyway, you don't need now to know the beta plus, beta minus, alpha decay. We will talk about all these reactions in the next chapters. Anyway, you have to know now the carbon decays to nitrogen by the emission of alpha by one electron, one emitted electron, and a small quantity of energy, neutrino, where you know neutrino is a small particle with a negligible mass. When I say we have a negligible mass, so we have a negligible kinetic energy. Just it's a small quantity of energy. Okay? Anyway, since the binding energy of carbon and nitrogen equals to 0.003242 U and 0.001374 U respectively. What is the maximum energy of neutrino? Before solving the problem, let me explain one point. Here, for example, I give you the binding energy in the atomic mass unit. Here, it's very important. In general, E equals to mc square. If you substitute the value of m by 1 atomic mass unit, you get E equals to 931.5 MeV. Okay? MeV. So here we have an equivalence between the mass, 1 atomic mass unit, and the energy. So if I tell you, for example, the weight of a bottle of water equals to 1 liter, it means we have 1 kilogram, because 1 liter is equivalent to 1 kilogram of water. So if I tell you we have 0.03242 U of binding energy, I mean we can say for each 1 atomic mass unit, we have 3931.5 MeV. So in the case of 0.003242 U, how much value of energy or how much value of MeV? Okay, X. So in this case, X must be equal to 0.003242 times 931.5 MeV. Okay, in this case, you can say directly when I give you the binding energy in the atomic mass unit, you can put it directly in MeV by multiplying by 931.5 MeV. So here, the binding energy of the carbon equals to 0.003242 times 931.5 MeV. We get the value in MeV. Like this, you can do the equivalent or the equivalence between the atomic mass unit of energy and the MeV unit of energy. The same for the binding energy of nitrogen, which is equal to 0.003074 times 931.5 MeV. Okay, now I want to find the maximum energy of neutrino. You have to know, anyway, it's an important problem. I can ask you find the maximum energy of neutrino, or I can ask you find the maximum energy of the maximum kinetic energy of beta minus. You can write here what is the maximum kinetic energy of beta minus. Okay, we have the same procedure. We can have the same solution to solve these two problems. In order to solve this problem, we have to do the energy balance, okay, for this reaction. Anyway, look here. The reaction here, we have the carbon 614 decays to nitrogen 714 plus 1, you know, 1 electrons. You can write E minus 1, 0, plus 1 neutrino. We have a conservation of energy. You know, for any nuclear reaction, we have many conservations laws or conservation laws. mc square of carbon plus kinetic energy of carbon. For each mass, we have some quantity of kinetic energy. But in general, when we have a heavy nuclei, the kinetic energy, it can be negligible. Okay, so we can say the kinetic energy equals to 0 because the heavy nuclei was at rest, or it has a small, relatively small kinetic energy. Okay, this is the total values of energy before the reaction, before the decay. And after the decay, we have mc square plus the kinetic energy of nitrogen plus m electron c square times the kinetic energy of the electron, okay, plus the energy of E. We cannot say here mc square of neutrino. We cannot say kinetic energy of neutrino because it's a very light particle. Just we can say we have some quantity of energy carried by neutrino. I want to find its maximum value. Okay, here we substitute the value of you know, mc square. M is the nuclear mass. The nuclear mass, you know, in general, binding energy equals to m ZMP plus n mn c square minus m n c square. So mnc square equals to zmp plus n mnc square minus binding energy. Okay, so we write here z and n c square minus binding energy of carbon of C equals to, we do the same relation for the nitrogen. We get 7mp plus 7mn c square minus binding energy of nitrogen n. Okay, plus mc square of 1 electron plus kinetic energy plus E of neutrino. You know, we can, here we have 6mp and here we have 7mp. So we can put 1mp here. It will be minus mpc square. Here we have 8mn and here we have 7mn. Finally, we get 1mnc square, and we can put here mec square minus binding energy plus the binding energy of nitrogen minus binding energy of carbon equals to E. Here, let me explain one point. In general, here we have E of neutrino plus kinetic energy of 1 beta. Okay, it's like this. You know, or you have to know that if we have of the general value of Q is divided between E of neutrino plus kinetic energy of beta minus. The value is constant. Okay. In the case of a maximum E mu, if we have a maximum E mu, so we have 0 kinetic energy of beta minus. And the opposite is right. If we have a maximum kinetic energy here, we have a 0 energy of neutrino mu. Okay? So here I can ask you, find the maximum value of the kinetic energy of 1 electron. In this case, you put here E neutrino equals to 0, and you can find kinetic energy maximum. And if I ask you to calculate E neutrino maximum, you have to put the value of the kinetic energy equal to 0. So here we have plus 0 in the case of maximum neutrino energy. Okay, we can substitute the value of the values of mp, mn, m of 1 electron. I gave you the values of bn and bc. Be careful here. You have to multiply by 931.5 MeV. Okay, in order to have MeV unit of the binding energy. You cannot have atomic mass unit for the binding energy. If I give you a atomic mass unit, you have to convert the unit to MeV. Okay? Okay, this is nothing. Just I explain this point. 1 AMU, atomic mass unit, is equivalent to 931.5 MeV. So here we can calculate the value of E neutrino maximum, and the unit will be MeV. Okay,